Welcome back to this module in which we extend the basic pipeline with multi-cycle operations. This lesson describes the challenges we face when the pipeline supports multi-cycle operations. Now that the pipeline is longer, we have some issues to solve. The first is, because the divider is not pipelined, structural hazards can occur. The canonical pipeline did not suffer from structural hazards. If you remember, we had to introduce them artificially by assuming there was only one memory port, but the longer pipeline does suffer from them and we need to solve them somehow. The second challenge is, because instructions now have different latencies, the number of instructions that want to write to the register file in a particular cycle can be larger than one. The third challenge is that the instructions do not always reach the write back stage in the order in which they were issued. Because of this, so-called write after write hazards may occur. Also, because instructions have varying latencies, they can complete out of order. Out of order means in an order different from the normal program, the normal thread order. This makes implementing exceptions difficult, and I will return to this issue in a later lesson. The fifth challenge is that because we now support longer latency operations, stalls due to read after write hazards will be more frequent. The final challenge that I will discuss is that the complexity of the forwarding logic increases if there are separate pipelines. On the following slides, I will describe each of these challenges in more detail and sketch potential solutions. First, structural hazards. As I said before, because the divider is not pipelined, there will be a structural hazard when two divide operations need to be executed shortly after each other. What can we do to solve these hazards? Well, basically there is no better way than to detect the hazard and stall the next divide instruction, as this example shows. We have a divide, then we have another type of instruction, in this case a subtract double, then we have a divide. When the second divide wants to issue, we have to detect that the divider is still busy and stall the second divide until the divider is free again. Is there really no better way? Can't we pipeline divisions or provide several dividers? Unfortunately not. For most applications, this solution will not be cost effective. Because two reasons. First, pipelining divisions or providing several dividers requires substantial amounts of hardware. And second, divisions are rare operations in most applications, which means that the extra hardware would be wasted. Compilers try to avoid such stall cycles by scheduling other operations between the two divisions. There's another potential structural hazard in our longer pipeline that is somewhat less visible. Because instructions have varying latencies, it may happen that multiple instructions want to write the register file in the same clock cycle. To see this, consider this example. The first instruction, a multiply double, writes to the register file in clock cycle 11. Then we have two arbitrary instructions indicated by ... And then in the fourth cycle an add double is fetched that also write back its result in clock cycle 11. Then again we have two arbitrary instructions, and then we have a load double that also wants to write the result in clock cycle 11. So we see that in clock cycle 11, three instructions want to write their result back to the register file. To deal with such hazards, we either need to stall or we should increase the number of write ports to the register file. If the register file has n write ports, then n instructions can write to it in a single cycle. Increasing the number of ports increases the complexity of the register file, however. Furthermore, this example is somewhat contrived, since in the current pipeline, instructions pass through the mem stage sequentially, meaning one after the other. And such structural hazards cannot occur if this is the case, since the mem stage basically serializes the instructions. Another issue for organizations with execution pipelines of different lengths is that write after write hazards are possible. A write after write hazard occurs when a later instruction writes to a certain register before an earlier instruction writes that very same register. To see this, please consider this example. The multiply double writes register F0 in clock cycle 11, and the next instruction also writes F0, but it does so already before that in time in clock cycle 9, because the add has a shorter latency than the multiply. Is this a problem? Well, not by itself, but a next instruction may read the wrong value. It may read the value produced by the multiply while it should use the value produced by the add. How do we solve this problem? Well, potential solution is again to stall the instruction that wants to write the same register as an instruction that is currently in flight. This means that if an instruction in the decode state wants to write the same register as an instruction that has already been issued, we should not issue the first instruction to its functional unit. One way, but not necessarily the best way to implement this, is to add a busy bit to each register. This bit is set in the decode stage and it is cleared in the write back stage. In the example on this slide, for example, the add double only needs to be stalled for 3 cycles instead of the full latency of multi-cycle operations. Luckily, instruction sequences such as this, 2 writes to the same register with no read in between, are very rare. Therefore, this simple method of dealing with such write after write hazards might be sufficient. Let's have a look at another example of a write after write hazard. In this example, first we have an add double instruction that is executed in these cycles, 1 to 8. Then we have an integer ALU instruction that is executed like this. Then we have a load that is executed in cycles 3 to 7. And then we have 4 arbitrary instructions that are fetched in cycles 4 to 7. And finally, we have an add double that is fetched, subtract double, that is fetched in cycle 8, reads the register file in cycle 9, and starts its execution in cycle 10. In this example, the subtract double should use the value loaded by the load double, as indicated by this red arrow. But when this instruction sequence is executed as shown here in time, the subtract will read the value written by the add double in clock cycle 8, as indicated by this red arrow. Instead of the value written to the register file by the load double in clock cycle 7, as indicated by this red circle. So to summarize, the subtract double will read and use the result written by the add double instead of the result written back by the load double, which is the result it should use. Let's consider this example once more. The first instruction is the add double that writes to F2. Then we have an arbitrary unrelated instruction. Then we have the load double that also writes to F2. And then we have 4 arbitrary but unrelated instructions to instruction 5. And finally we have the subtract double that uses F2. If we look at this code carefully, then we see that the result of the add double is, as it should be, overwritten without any instruction using the result. In fact, in the current pipeline, a write after write hazard occurs if and only if a useless instruction is executed, whose result is never a use. That doesn't make any sense, does it? Why should the assembler programmer or the compiler generate useless instructions? Can't we simply assume that useless instructions are never executed? Unfortunately, the answer is no. We must detect the write after write hazard and provide correct execution. But why? I give you 5 seconds to think of an answer. Don't panic if you didn't find the answer. It's quite intricate. It has to do with the famous branch delay slot. The compiler might move an instruction into the branch delay slot that is useful on one branch path, but useless on the other path. This is illustrated in this example. The branch not equal 0 branches to the instruction at label foo if the branch is taken. The compiler expects this branch to be not taken and therefore has scheduled the divide from the not taken path, in other words, the fall through path, in the branch delay slot. The fall through path is indicated in this code snippet by ... If the branch is taken, the divide will also be executed, but its result is never used since the low double that also writes to F0 overrides the result. So this is a potential write after write hazard that the hardware must detect to provide correct execution. Another challenge, and perhaps the greatest challenge for longer pipelines, is that stalls due to read after write hazards will be more frequent than in the canonical 5-stage pipeline. A read after write hazard occurs when an instruction reads a register that is written by a preceding instruction that is still in the pipeline. Because of this, the dependent instruction has to stall until the result is available. I will illustrate this again by an example. The first instruction is a load that writes to F4. The second instruction is a multiply that reads F4 and writes its result to F0. The third instruction is an add double that reads F0 and writes F2. And the third and the next instruction is a store double that reads F2. So we see that every instruction depends on the previous instruction. Then the first instruction is executed like this in these cycles. Since it is the first one that is issued, it executes without stalls. The second instruction uses the result of the first and is executed like this. Because the result of the low double is available only at the end of the mem stage, the multiply has to stall in its decode stage before it can be issued to the multiplier pipeline, as indicated by the light blue colored and crossed box. This corresponds to the by now well-known load use data hazard. Then the add double executes like this. It can be seen that it incurs many stall cycles, 6 to be precise. First, because the multiply stalls in its decode stage, the add needs to stall in its instruction fetch stage, since at any time there can be only one instruction in its instruction decode stage. Second, because the add uses the result of the preceding multiply, and this result is not available until the end of the multiplier pipeline, it has to stall in its instruction decode stage until the result is available, which is after the 6th multiplier stage, M6. Note that in this pipeline diagram I assume that the result can be forwarded from the M6 stage to the first floating point adder stage A1. Finally, the store double is executed in these stages. It also suffers from many stall cycles. First it stalls in its fetch stage. As before, because the add stalls in its decode stage, the store must stall in its fetch stage, since at any time there can be only one instruction in any pipeline stage. The store also stalls in its execute stage. The first two stalls are due to the fact that the value to be stored is not yet available, but is being produced by the floating point adder. After these two cycles, the result could in principle be forwarded to the mem stage of the store. However, another stall cycle is required because the add and the store currently assumed cannot be in the mem stage at the same time. In other words, the mem stage will serialize these two instructions. So the conclusion that stalls due to read after write hazards occur more frequently in longer pipelines than in shorter pipelines is well justified. In the next lesson, I will show what the compiler can do to avoid these stalls. Another challenge for longer pipelines is that the complexity of the forwarding logic increases. Basically, we must check if the destination register in any of the pipeline registers xmem, A4/mem, M7mem, diffmem, or mem/writeback is equal to one of the source registers of a floating point instruction that is currently in execution. I hope you remember that pipeline registers are used to separate the pipeline stages and are named after the two pipeline stages they separate. Note also that I have added a question mark after xmem, because in my opinion the destination register in this pipeline register cannot be the source register of a floating point instruction. It depends if the integer unit also performs integer to floating point conversions, or if the multiplier and divider also perform integer operations, then forwarding from the xmem pipeline register is also needed. In this figure, I will try to sketch how forwarding to floating point instructions can be implemented. The figure shows the execution units and the final pipeline register at the end of every execution pipeline. First, we need very large multiplexers in front of every floating point unit. These multiplexers select between the values that were read from the floating point register file in the previous cycles during the decode stage and the results that have been computed in the previous cycle. So inputs to these multiplexers are the values read from the floating point register file in the previous cycle and the results contained in the pipeline registers at the end of every execution pipeline, as shown by these many wires. Hopefully this convinces you that a lot of wiring and large multiplexers are required to implement forwarding in longer pipelines. To keep the figure relatively simple, I have even omitted forwarding from the mem writeback pipeline register, as indicated by this loose arrow, and more importantly, I have omitted the hardware that checks if the destination register is equal to one of the source registers of the instruction currently being issued. The main point I would like you to take home is that having longer and multiple execution pipeline increases the complexity of the forwarding logic significantly compared to the forwarding logic in the canonical 5-stage pipeline. This completes this lesson. Thank you for watching. In the next lesson I will describe the MIPS R4K pipeline consisting of 8 stages. Hope to see you back.